Hey everyone, welcome to part two of Igneous Rocks. So today we want to do, I think, a few things. We want to talk about how to make magma. It's not as easy as you think. We want to talk about Bowen's reaction series, which is a very important thing that we will be referring back to pretty much for the entire rest of the semester. And then we want to talk about igneous structures, and so that will wrap us up. I'm not planning on this being a terribly long lecture, and so I will probably not put a break in it. Hopefully I won't go on too much, so we should be okay with just the length of this lecture. But if you need to take a break, hit the pause button, walk around the room, get some water, get some coffee, whatever works for you. Okay, so let's make some magma. So the reason, obviously maybe this is important is because igneous rocks form from molten rock. So where does that molten rock come from? Well, a lot of people think, well, it comes from the mantle because the mantle is molten rock. No, it's not. Mantle is solid. The mantle is solid rock. It flows because it's hot and it's under pressure, but it is a solid that will flow. And if you're confused about solids that flow, think about Play-Doh, another solid that flows. Okay, so it's not as simple as, well, let's just bring some mantle up because it's liquid and that's magma, and it doesn't work that way. And so we need to heat the rock or something. We need to do something. It's just not going to be as simple as bring the mantle up. And so here's the problem, though. So take a look at this. Let me get my pointer back here. I'm going to draw on this in a second, but let me just get my pointer back. So take a look at this diagram. So what we're graphing here is temperature on this axis and then depth down through here. And as you go down, the pressure increases, right? Geologists, we love drawing graphs like this, right? Because you can imagine you're standing right here and, you can kind of imagine what's going on under your feet as you go down through the earth. Oceanographers also do a lot of graphs like this. So anyway, so this line right here is what we call the geothermal gradient. That's the temperature that rock is at that depth. Another way of thinking about it is, if I was to bury a rock, this deep, let's say 100 kilometers down, how hot would it be? Well, it would be just over 1,000 degrees Celsius, right? If I was to, bury a rock 300 kilometers down, it would be closer to 1,500 Celsius, etc., right? And so as you go down, it gets warmer, the rock gets warmer, and this is, what that curve looks like. Now, maybe you've been to a cave and you're about to say to me, hey, wait, when I went to, Florida Caverns or something like that, it was cooler inside that cave. Yeah, it was, but you weren't that far down. Okay, right, those caves are cooler because they're out of the sunlight. And they are very nice and cool because they're never in sunlight. But, that's you're not that far down. You're like, I don't know, 100 feet maybe. That's not even on this scale. That's 100 kilometers, 62 miles. Okay, so yeah, your cave doesn't count. Okay, but mines do, like really deep coal mines or other resource mines. Absolutely, they have to deal with this. It gets hot for those miners, and cooling those mines is a whole thing. Now here's the thing, though. So here's the temperature at depth where you would need to heat rock to get it to melt, right? Because as you go down, the pressure increases. And because the pressure increases, the temperature that rock will melt at also increases, right? At the surface, and they're doing peridotite, and that's fine. At the surface, we'll talk more about that later. At the surface, that rock will melt at just over 1,000 degrees Celsius, okay? At 200 kilometers down, it's closer to, it's around 15, maybe, I don't know, maybe 12, 13, 1400. Okay, so that melting temperature is higher, right? As you go down, the pressure increases, and that increases the melting temperature of the rock. Notice this. this line that represents the temperature that the rock is, never crosses that line, right? This line here, which means you can't melt rock by burying it. Right? You can bury it as deep as you want. It will not melt from the heat, from the geothermal gradient, right? And so let me draw here. And so let's say that I have a rock. Let's see, I got my little drawing pad here. Let's say that I have a rock. Let's say I have a rock that's buried, 100 kilometers down, right? And so my rock is buried, and it's, I don't know what I did. There we go. My rock is buried right there. Okay, so it's actually, now see, it just slid over into the partial melting zone. That's not good because it's not going to melt, right? So if I have a rock, let me be a little more precise. If I have a rock that has done that weird thing again. If I have a rock that is right here, okay, so it's 100 kilometers down. That means that it is 1,000, 1,500. That's 1,200. That's about 1,300 degrees. If it was on the surface, I don't know why I keep doing that. If it was on the surface, it would melt, right? If I just had an oven that went that hot, went to 13, 1,400 degrees, that rock would melt. But it's buried, right? It's under more pressure, so it's not going to melt. Okay, and in fact, there's nowhere, as you can see, along this line where that rock's going to melt. Okay, so how do we get rock to melt? Well, there's two possibilities here, right? The first, kind of maybe obvious one, is find a way down there to heat that rock, right? To move it. Sorry, guys. Let's go back. There we are. Let's find a way to move that rock this way, right? Let's find a way to increase the temperature of the rock and move it that way. We can do that by exposing it to some igneous rock. Maybe an igneous intrusion pushes through and heats the rock or something like that. And that's certainly possible. It happens, but it doesn't happen that much, and that usually happens up in here anyway. So heating the rock more beyond the geothermal gradient is certainly possible, okay, but not terribly common. What is oddly enough more common is to physically, that keeps doing that, is to physically, pretend I'm drawing a straight line, physically move the rock up, right? If I move the rock physically from 100 kilometers down to, 50, 25 kilometers down, now it crosses that line and it melts. Right, and so what we need, so really more than heat the rock, which you can do, but it's not going to, you're not going to make a volcano from heating the rock down there, that with an igneous intrusion or something. That's not going to work. Okay, what you're more likely to do is physically move the rock up. Right, if I move the rock up without changing the temperature of the rock, it crosses this line and it ends up melting. Okay, so where do we do that? How do we do that? Right? What's going on here? Now I'm going to come back to this, so I want to delete this off of here because I know I'm actually planning ahead. I'm going to come back to this drawing. But we can, what we want to do, and I just deleted it, but I'm going to draw it again. We want to move the rock up, right? Oh, that's a better arrow. We want to move the rock up. Okay, so where do we do that? Well, how about a mid-ocean ridge? Right, so here, we've got convection moving the mantle, the solid mantle up. Okay, and when we do that along a mid-ocean ridge, right? Let me go back to I don't need to draw on this, so let me go back to my pointer. Along a mid-ocean ridge, right? You're pulling rock this way, you're pulling rock that way, that draws that mantle, that solid mantle that will still flow up, okay? And when it comes up, the pressure is released and it melts. And so now you have, volcanoes along these mid-ocean ridges like you do in Iceland and, Africa, places we talked about where you have these divergent plate boundaries. So yeah, at divergent plate boundaries, You got, lithosphere crust moving this way, lithosphere crust moving that way. That draws the rock up and causes it to melt because the pressure drops, right? This is called decompression melting, okay? And so, right, so what we're doing here on our graph is we're taking rock that is down here, we're drawing it up, and it melts, and bingo, magma that will cool into igneous rock, right? And so what we're doing here really is we're lowering the pressure. Okay, now, so that's one way to do it. Here's the other way though, and I need to draw again. I'm gonna have to draw a line, so you are gonna have to bear with me here because this could get ugly. Okay, so let me get rid of my arrow. And there. Okay, so here's the trick. This is the melting curve for mantle rock, and that's fine. We don't. The difference between. Let's not worry about that. But here's what we do need to worry about. This is the melting curve for dry. My writing is awful. Dry mantle rock. Okay, wet rock is easier to melt. Wet rock will melt at a lower temperature. Okay, now I'm going to put a line on here. I don't want you to make too much of it because I don't know what the temperatures actually are offhand because I'm not an igneous person. But the melting curve for dry rock, is somewhere over here. Okay, and looks, something like that. Once again, please don't think that, don't pay attention to this. Don't just get the general idea, right? That the melting curve for wet rock is displaced this way, right? It's easier to melt wet rock, or you don't have to heat it as much. Okay, so if the rock is wet, the geothermal gradient will do it. So where do we go to melt wet rock? Well, how about an ocean continent convergent plate boundary? Right? Because here, what you've got, and let me get back to my pointer, what you've got, right, is you've got oceanic crust. It's all cracked. There's water all in this, right? It's underwater. Okay, any crack is going to have water in it. It's going to water all in it. And so now, when it goes underneath the continental crust, now the geothermal gradient does melt it, okay, because it's wet, right? And let me go back to the graph. It's wet, and so now, just burying it will actually melt it. And it occurs to me that my drawing might be a wee bit confusing because of my arrow. Let me just make it clear that. There we go. Let me just make it clear that this arrow here is wet, right? That lousy little line that I drew right there is wet, right? This curve right here is dry. Okay, and so what this shows us is, if the rock is wet, you can get it to melt at a convergent plate boundary, right? Because you go down. Whoops. Sorry, went back too far. My trackpad is being weird, and I don't have my mouse, so I can't lock it out. Anyway, so down right here, you can melt rock by burying it because it's wet, right? And so you melt it. The rock rises, and we get volcanoes on the back side, like our Cascade Range volcanoes, or the Andes Mountains, or something like that. Okay, so that's magma generation in a very small nutshell. Now, here's the thing we need to get, and that is that a magma. Let me go back to my pointer because Anyway. Magma consists of a lot of different elements that are going to arrange themselves into different minerals. And those minerals have different melting points or freezing points. Now, when I say freezing here, don't associate that with a temperature. Associate that with a change of state, right? So we're going to go from liquid to solid, right? That's what I mean by freezing, okay? When we say the word freezing, normally we mean the freezing temperature of water, which is cold, Okay, everything has a freezing and a melting temperature. Not all of them are cold at all. Right? In fact, most things around you are not. And so olivine has a freezing temperature that is considerably warmer than quartz does. Right? And so if you have a magma that is full of all these chemicals that are going to arrange themselves into minerals, different minerals are going to form at different temperatures. Okay, and so I'm going to go back to my. No, I don't want to highlight. Highlighting is stupid. I want to go here. Okay, so right, and so as that magma cools, okay, the first thing that's going to crystallize out of it is the mineral olivine. Okay, after that will be the mineral pyroxene. And I know you're like, what? Don't freak about the minerals, okay? And then after that will be the mineral amphibole. After that will be biotite mica, followed by down here potassium feldspar, muscovite mica, and then the last thing will be quartz. Okay, we call this, and this is a sequence that geologists, we have tattooed on our eyelids. We can recite this no problem. Olivine, pyroxene, amphibole, biotite mica, potassium feldspar, muscovite mica, quartz. We just know it. Okay, here's some actual temperatures. So high temperature, so this olivine is going to come out at about 1200 degrees Celsius. Okay, this quartz is going to come out at about 750 degrees Celsius. Okay, but I'm not as concerned with the temperatures as I am with just the idea that if I have a liquid magma, right, the olivine is, and it's cooling, the olivine is going to cool out first, followed by the pyroxene, followed by the amphibole, followed by the biotite mica, then potassium feldspar, muscovite mica, and quartz. Okay. Now, at the same time, over here, we have what's called a continuous reaction series. This over here is what we call discontinuous reaction series, because you go olivine, then you go pyroxene, then you go amphibole, then you go biotite mica, etc., etc., etc. Okay. Over here, you've got a mineral called plagioclase feldspar. Plagioclase feldspar can be either calcium rich or it can be sodium rich. Okay, if your magma is cooling, the first plagioclase feldspar to solidify is going to be the calcium rich version, and then as the magma continues to cool and minerals continue to solidify out of it, you get more and more and more sodium, right? So as that magma cools, you add sodium to that mineral. And I'm going to pause for 1 second and find you guys a picture. I will be right back. Okay, I'm back. So it deleted all my annotations here, but that's fine. So remember that we have this, I just showed you what I was getting to. Hold on 1 second. We'll get to that in 1 second. So remember that we have this discontinuous reaction series over here. My pin's a different color, which is freaking me out. There we go. Discontinuous reaction series over here, where we go from olivine to pyroxene to amphibole to biotite mica, potassium feldspar, muscovite, and quartz. And then a continuous reaction series over here, where we have the mineral plagioclase feldspar. And what we do is we just add sodium, right, as the magma cools. Pretend that's an A, not a G. We just add sodium as the mineral cools, right? And so, or as the magma cools, rather. And so what that gives us sometimes is this. This is a piece of plagioclase feldspar that is what we call zoned. Now, the light passing through here is funny. It's polarized. It's doing weird things. Don't make too much of colors or anything like that, but you can see these bands in it, right? And as this mineral has cooled, we've added, or we haven't, but the magma has, or the mineral has added more and more and more sodium to this mineral as it cools in this magma, and this produces these really striking compositionally zoned minerals. So really, really cool. And like I said, what we're doing here is we're adding sodium as the mineral cools. So this bit in here that cooled at first is calcium rich, right? And then the bit out here is more sodium rich. So you can literally go from one to the other in the space of one mineral cooling. And let me go back because I want to get my words back so you can see them if you want to. This is so important though. Because Bowen's reaction series explains so many things, right? First of all, as you can see, up here, the olivine, the pyroxene, the amphibole, the more calcium-rich feldspar tends to make rocks that are mafic to ultramafic in composition, right? Down here in the middle of Bowen's reaction series, we've got some amphiboles, some biotite mica, and then some plagioclase feldspar. These tend to make rocks or magmas or whatever that are a little more intermediate in composition. And then down here at the end, you get rocks that are more felsic in composition. Now, there's also quartz. Don't pretend that quartz is only down here. Quartz is everywhere, right? You will find isolated, cooler parts of the magma that will precipitate quartz just about. Actually, my arrow is pretty good because when you get into ultramafics, maybe not, but just about everywhere you're going to get some quartz. But here's the other thing, right? And I'm about to make a mess of this diagram because there's so much stuff you can add on here, right? Up here are your, now just point rather than draw. Up here are explosive volcanoes. Let me get back to pointing. Up here are explosive volcanoes. Or rather, I'm sorry, I got that backward. Up here are not explosive volcanoes like Hawaii. Down here are explosive volcanoes like Yellowstone. In here are explosive but not horrible volcanoes like Mount St. Helens, right? And so, the explosiveness of the volcano. Less explosive up here, more explosive down here. If it's the magma, not a rock, obviously. It needs to be a magma. Also, how fast will the mineral break down? Minerals up here break down very, very quickly. Minerals down here don't break down quickly at all, and we'll talk about that when we talk about sediments. When you go to the beach in Florida, it's pretty much all quartz. Right? By the time it gets to the beach down there, it's pretty much all quartz. So chemical weathering, lots of chemical weathering up here, not so much chemical weathering down here. Physical weathering works the same way. These break down physically and chemically much more quickly. These much more slowly. It just goes on and on and on and on. And so this is something that's very important that we'll come back to over and over again. If I've got a magma that is cooling, olivine first, then pyroxene, meanwhile calcium-rich plagioclase feldspar, amphibole, biotite mica, more sodium, more sodium, more sodium over here, potassium feldspar, muscovite mica, then quartz. Okay, now here's the other trick. It works the other way too. If I have a magma that is cooling, this is the order from top to bottom that the minerals will freeze at. Okay, if I have a rock that is melting, just go the other way, right? If I have a rock that's melting, the quartz will melt first, then the muscovite mica, then the potassium feldspar, then the biotite, etc., etc. Olivine will be the last mineral to melt out of a rock. Okay, along with calcium-rich plagioclase feldspar, right? And this is just because minerals are pure substances. So that's what a chemist would call a mineral, and so it has a very distinctive melting temperature. Okay, and they're different for different minerals. And so once again, I'm going to say it one more time, and then I promise I'll move on. If a magma is cooling, olivine first, followed by calcium-rich pyroxene, amphibole, biotite mica. Meanwhile, plagioclase feldspar was going from calcium, more and more and more sodium, less and less and less calcium. Sorry, I should have put a little minus Ca there too, but I won't. Then potassium, feldspar, muscovite, and quartz, right? So if a magma is cooling, it goes this way. You could have easily, although I've honestly never seen one like this, you could draw the arrows in a different direction, right, and call that melting. right? And so first quartz, then muscovite, mica, potassium feldspar, biotite, amphibole, pyroxene, olivine, sodium, decalcium, rich plagioclase, feldspar, right? And so this turns out this is a very important diagram, and I will be referring back to this as we go. So there's our compositionally zoned feldspar or plagioclase feldspar. So this sets up some interesting things. Okay, two things. First of all, crystal settling, right? There are actual physical things that happen, manifestations, if you will, of this chemistry. So if I have that magma chamber and it begins to cool, right, the mafic minerals, olivine, pyroxene, calcium-rich plagioclase, etc., are going to turn solid first, and they will literally sink down to the bottom of the magma chamber. So you'll get a layer of mafic minerals at the bottom of that magma chamber. Meanwhile, though, the remaining magma is more felsic, right? It's more silica rich. And so this is important, right? This is very important because this is where we get continental crust from, right? When the Earth first formed, it was covered in water, right? There was no land, okay? I mean, it was mafic rock covered with water. Okay, so how are we going to get continents? Well, plate tectonics kicks in, which is kind of glossing over some interesting stuff, but plate tectonics kicks in, right? We get a plate boundary, a convergent plate boundary, let's say, right? We generate some magma, and what's going to happen? Well, the mafic minerals are going to settle out, okay, leaving behind a more felsic liquid. If we can separate that felsic liquid from that magma chamber, and that's not hard to do, suddenly it comes to the surface, it's less dense, it's thicker, it's all the things that continental rock are, right? And you do that enough, and you will gradually, very gradually, make continents, right? But this is the process that does that. Partial melting produces a set of mafic minerals along with felsic liquid, right? And then if you can separate that felsic liquid, and once again, that's not hard to do, you'll have a felsic rock. You'll make a granite. Right? Well, that granite is, the rough chemical composition of continental crust. And so this process is very important. If it wasn't for this process, we would not be here because our planet would not have any continental crust on it. Okay, so crystal settling produces mafic solids and felsic liquids, right? Those felsic liquids can cool to become felsic rock. Now, going the other way, it works too. If we go the other way, if we take a solid rock and we melt it, right? I read and thought something and my brain just went away. Okay, if you heat a rock, the felsic minerals will liquefy first, right? They will melt first, okay? So once again, now I have felsic liquid. Right, that felsic liquid can go somewhere else and make felsic rock, and then what's left behind are the mafic minerals. And if I heat it enough, I'll eventually melt those mafic minerals. But if I don't, what I'll end up with is a felsic or an intermediate liquid with some mafic residue left behind, right? But both crystal settling and partial melting will produce, let's say, a more felsic liquid and a more mafic solid residue. Okay, and so both of these processes, serve to turn mafic rock more into intermediate rock and more into felsic rock, which is good because felsic rock is land, right? Felsic rock is what we live on, and so when we think about planetary evolution, this is an important thing. Planets generally begin as mafic, and I know our moon's not a planet, but we got rocks from there, and they're mafic. They're mafic. And so that makes sense. Rocks from Mars, we don't have any brought back from Mars yet, but Mars is kind of interesting because those rocks might not be as mafic as we would think they should be, and Mars has no plate tectonics. So, yeah. Yeah, there's a whole field called planetary geology, and if you want to be a planetary geologist, there's an interesting question for you right there. Okay, so now, when these igneous, these magma chambers or whatever, cool underground, they're called intrusive, and those bodies of rock underground are called plutons. And way back during the Pluto kerfuffle, when astronomers were trying to decide if Pluto was a planet or not, and I'm putting little air quotes around planet, there was some talk for a little bit. Let's call it a Pluton, and all the geologists, we raised our hand and says, no, you can't have that word. We're already using it, and it's actually kind of named for the same god of the underworld, and so kind of fascinating that way. So anyway, if we think about bodies underground, some of them are just kind of blob shaped, and I'm going to go skip to this picture here where you can see that we've got, this magma chamber and this magma chamber and this thing here, these kind of blob shaped plutons, and we have two kinds. We call those massive, by the way, not blob shaped, but we call those massive, and there's two basic kinds, batholiths and laccoliths. And so if we look at this drawing here again, we can see that these underground magma chambers, if they cool underground, like let's say Stone Mountain, and I don't honestly know if I have any pictures or not. Let me just see something real. Yeah, there we go. Right, Stone Mountain. Here we go. Cooled underground, right? And so this is a batholith. Okay, this was never a volcano. Okay, it cooled completely underground. Never a volcano. And I was at Stone Mountain just a couple weeks ago. Stayed at this hotel. It's a really nice place, by the way. Anyway, cooled underground. Okay, so that's called a batholith, right? And I'll show you that other picture here in just a moment. So let's think a little bit about how these form. Okay, and then we'll talk about dikes and sills for a second here. But so you've got a region with a lot of igneous activity. Some of these magma chambers will breach the surface to make volcanoes. Some of them won't. Okay. Eventually, the forces that are causing this magma to be generated will stop. And so what will happen then is erosion, right? And this is what happened out at Stone Mountain. I think I talked about this, how, it's a coarse-grained, phaneritic igneous rock, and yet it's exposed at the surface, right? Erosion, right? That happens a lot. And so you have these magma chambers down here that will be called batholiths, and then you've got this thing here called a laccolith, where you have a tube of magma coming up, and it pushes the overlying rock up, right? It inserts itself into that rock, and you get this upwardly bowed rock, and that magma chamber is called a laccolith. Well, once this volcanism shuts down, then erosion begins, right? And you'll get what's left of that laccolith. You'll get these volcanic peaks, kind of like Shiprock, Arizona. Give me 1 second. I'm going to go find you a picture of Shiprock, Arizona. Be right back. Shiprock is in New Mexico, not Arizona. How strange of me. Having been there, you'd think I'd know what state I was in. Anyway, so a lot of times, with erosion of these volcanic terrains, you'll get things that look like this and this. There we go. And that's shiprock. Okay, so called because from a distance, I guess to some people it looks like a ship. But anyway, I don't see it personally, but okay. But that's a volcanic neck, right? That's an ancient volcano that got plugged with igneous rock in its vent. And then erosion exposed that and obviously broke that down a bit too. And so this is very common out west. In fact, whenever you see like these large, not really rounded over bodies of igneous rock like this, odds are that's what they are. And so And so, oh, too far. There we go. And so, initially as you begin eroding this, you'll get these remnant volcanic necks sticking up. And I'm going to talk about dikes and sills here in just a moment. But let's go on for a bit and see some other things. So if we continue to erode, right, what you end up with is all of this rock that was exposed, because of erosion, that was underground, that was then exposed by erosion. Now they're drawing arrows upward here. I think that's kind of stupid because that's not moving. Right, what's happening here is the surrounding rock is going down. So what we really need are down arrows here on this surrounding rock. These are not moving up. They're just not. Okay, once they cool, they are in place and you're done moving. Okay, if we go out to Yosemite, we can see this, right? We can see this entire landscape of igneous rock that's made from eroding down to that previously underground rock. And once again, Stone Mountain is the same thing, just not on so grand a scale. Although when you're there, it is pretty dang big, I tell you. But Stone Mountain is the same thing, though, except it was a reasonably isolated body of magma, working its way up a little bit before cooling underground and then being exposed by erosion. And so, yeah, so at the same time, let's go back. I should probably put that slide in there, but that's okay. So let's go back here, and we can see that as these magma bodies, when they were moving upward, so back here, okay, they're injecting magma into the surrounding rock, right? And so a lot of times you'll get cracks in the rock or whatnot, things that will work their way in. Or rather, magma will work its way into those cracks. So this is pretty simple, really. When the magma is working its way across the surrounding, what we call the country rock, we call that a sill. Right, and so this is a sill. These are sills. Are all of these bodies that are working their way across the country rock are called. I'm sorry. I got that wrong. Mostly because I'm going to blame the labeling on here. Okay, let's go back, and let's go back. Okay. Magma that works its way across the surrounding country rock is called a dike, and I apologize. I feel like their diagram is labeled funny, and that threw me off. Sorry, guys. So anyway, so once again, ignore what I said before. Ignore it. Apparently, I need another cup of coffee. I'll go get it as soon as I'm done. But igneous rock that's working its way across the surrounding rock is called a dike. Okay. Igneous rock that is working in between the layers of country rock, those are called sills, right? And so you got a kind of a two-dimensional drawing here showing, this rock cutting across the country rock, that rock cutting across the country rock. Those are all dikes. They've got arrows drawn here and here that I probably should have paid attention to so as not to mess it up. Meh. Okay, so igneous rock cutting across the surrounding rock is a dike. If it's injecting itself in between the layers of country rock, that's called a sill. Okay, so dikes go across the country rock, sills go in between the country rock, right? And so when we cool this all the way, right, we got solidified magma down here. We've got these what we sometimes call swarms of dikes when you get a lot of them working their way up here. You can get those dikes breaching the ground surface, especially when there's erosion, and they will a lot of times, almost all the time, end up sticking up above the ground surface. And this is the case at Shiprock 2. I'll show you here in just a moment. And so dikes are running across the country rock, and they frequently stick up and make these walls in the landscape. And then sills are running in between the layers of country rock, and they end up kind of looking, let me show you, they end up looking like that. Right, where you have this sedimentary rock, and then there's a layer of basalt, right, squeezed into, because there should be more sedimentary rock on top of this. It's been eroded away. This isn't a lava flow, because when you look at it, it's intrusive, right? It's phaneritic. It's not a lava flow. It's a sill, right? It pushed its way in. Here's another one here, and it pushed its way in between that rock. In fact, that sill and that sill are probably the same thing. And you can see that if we walk over here, there's more rock on top of it. And so sills run parallel to that country rock, and they tend to expand things and stuff like that. Dikes, on the other hand, and this is shiprock. Dikes, and there's a dike right there. Dikes run up and down, right, across the country rock. And when they do breach the surface, they tend to make these wall-like structures, because that igneous rock is a lot more resistant to erosion than the surrounding country rock is, right? And that's kind of a dead giveaway that peak is a volcano, because a lot of times might not look like, you're like, is that a volcano? Yeah, well, there's a dike. There's a very, very distinctive dike running into it. So, yeah, odds are it is some kind of a volcano. So these are very, very useful structures. And when you go out west, you see this a lot. And I'm going to grab a Google Earth image of shiprock. I'll be right back, and that'll be the last thing we'll look at. I'll be right back. Hello, everyone. Okay, so here is Shiprock, New Mexico, not Arizona, sorry, on Google Earth. And you can see that volcanic peak there. And in fact, if we can also see a nice big obvious dike right there, and a nice big obvious dike right there that we're feeding that volcano. If we kind of go down a bit, we can zoom in a bit, we can see it in fancy, I don't know, video game looking 3 dimensions, but there it is. Now, there's two kind of obvious dikes, but as I was doing this, I was like, wait a second, right? There's a less obvious dike right there, and here's a less obvious dike over here. So there's, and if we looked really hard and maybe got some side scan sonar out there or something, we might be able to find some other stuff, or some, not side scan sonar, sorry, ground penetrating radar out there. We could probably find some other stuff. So interesting stuff. But if you ever get a chance, definitely check out Shiprock, New Mexico. It's really very cool. It is near the town of Shiprock, named after the volcanic feature. But we can see here a nice volcanic neck, remnant neck from previously active volcano, and then we can see an obvious dike over here that used to feed that volcano, an obvious dike over here, a less obvious dike there, and a less obvious dike there. And so it's really a fascinating place. Okay, that'll wrap us up for igneous rock. So I'm going to go ahead and compile this and get it up, and I'll shoot you guys an email and let you know it's up there. Okay, everyone take care. If you're in lab, at this point the lab is up, so go check that out. Okay, bye-bye.